In this video, we're going to look at a really interesting integral. So it goes like this. It's the integral from 0 to infinity of the natural log of 1 plus x times the natural log of 1 plus 1 over x squared all over x dx. And so along the way, we're going to see the following things feature in this solution. So the first is going to be transformation into a triple integral. Then we'll also use integration by parts. We'll do an infinite series expansion. We'll also see the Riemann Zeta, Dirichlet eta, and Dirichlet beta functions. And finally, this thing called the Catalan constant. So this integral really provides us an opportunity to review and learn about a lot of different things. Now, along the way, we're going to prove these 4 bullet points in order to make our solution a little more smooth. So the first one will be the following integral. So 0 to 1 of 1 over 1 plus x times y dy is going to be this function natural log of 1 plus x over x. So notice that's that. Then the integral from 0 to 1 of 2z over z squared plus x squared dz is the natural log of 1 plus 1 over x squared. So that's going to be that function. So these 2 bullet points will really tell us how to transform into a triple integral, as we will see. Then we'll use integration by parts to prove this formula. So the integral from 0 to 1 of t to the m, natural log of t, is 1 over m plus 1 squared, and it's negative of that. And I should say here that m takes on certain values, positive integers, but it doesn't really matter in this case, as we'll see in our solution. And then finally, we'll use this fact that the Dirichlet eta function, which is sometimes called the alternating zeta function. So notice it looks exactly like the Riemann zeta function, except for it's alternating instead of just being a straight sum. And so it is equal to 1 minus 2 to the 1 minus s times the zeta function. Okay, so I'm going to clean up this board, and then we're going to get to proving these bullet points. But I want to try to clean up this board in a way that I haven't done in a while. Let's see if it works. Oh, it seemed to work. So let's get to proving this first bullet point, which is actually quite simple. So we're going to look at the integral from 0 to 1 over 1 plus x times y dy. Now, you can do a little baby u substitution if you want to do this. So maybe we would let u equal x times y. And notice here our variable of integration is y. So that means when we take du, we will get that this is x dy, which tells us that dy is equal to 1 over x du. But now that means this dy turns into 1 over x du. And here notice that this is u. And now let's see what happens to our bounds of substitution. So recall that these are y numbers right here. So when y equals 0, that tells us that u is also going to be equal 0, and y is equal to 1, that tells us that u is going to be equal to x. So that's going to change this thing into the integral from 0 to x of 1 over 1 plus u times du, and then we can put a 1 over x out in front because that is a constant with respect to the integral. But notice now we're pretty much home free. This is going to be 1 over x times the natural log of 1 plus u evaluated from 0 to x. Notice evaluating at x gives us natural log of 1 plus x over x. And evaluating at 0 gives us the natural log of 1, which is equal to 0. So that means we have proved this first bullet point. And now we're ready to move on to the proof of the second one. So here we have the integral from 0 to 1 of 2z over z squared plus x squared dz. Okay, so again, this is going to be an integration with respect to z, so that makes x squared a constant. So let's do a baby u substitution again. So let's go ahead and in this case, we'll let u equal z squared plus x squared. But notice that is going to make du equal to 2z dz. So notice this numerator, those are my du earmuffs. And then this whole denominator is equal to u. Great. Now let's see what happens to the bounds of integration. When z is equal to 0, that means u is going to be equal to x squared. And then when z is equal to 1, that's going to make u equal to 1 plus x squared. Great. So let's see what that does. This is going to change it to the integral from x squared to 1 plus x squared of 1 over u du. So that's going to give us the natural log of u evaluated from x squared to 1 plus x squared. Great. But that's going to give us the natural log of 1 plus x squared minus the natural log of x squared. But now using logarithm rules, that's going to be the natural log of 1 plus x squared over x squared, which is the natural log of 1 plus 1 over x squared. Okay, so that means we've established this second bullet point, and now we're ready to move on to the third. So for the third bullet point, we want to look at the integral from 0 to 1 of t to the m natural log of t dt. And we can just assume that m is bigger than or equal to 0 here. That's actually the case that we're interested in. Okay, so in this problem, we'll use integration by parts. So that means we need a u and we need a dv. And so we need to choose u so that when we take its derivative, it becomes simpler. So a good choice there will be u equals the natural log of t. So let's say u is equal to the natural log of t. So notice that's going to make du equal to 1 over t dt, which means v will be equal to t to the m. dv will be equal to t to the m dt, but that is going to make v equal to 1 over m plus 1 t to the m plus 1. Okay, perfect. Now if we recall our integration by parts formula, we have u dv is equal to uv minus v du, where we plug in the bounds of integration as appropriate. Okay, so let's see what we get from that. So we're going to get u times v, so that's going to be a natural log of t over m plus 1 times t to the m plus 1, evaluated from 0 to 1. And then we will subtract from that v du. So notice that is going to be 1 over m plus 1. I can bring that out of the entire thing. And then the integral from 0 to 1 of t to the m dt. So notice we have t to the m plus 1 over t, which just makes t to the m. Okay, good. Now notice if we plug 1 into here, we get 0 because natural log of 1 is 0. If we plug 0 into here, we also get 0 because obviously t0 is 0. And you might say, well, if you plug 0 into the natural log of t, that's actually tending towards negative infinity. But it's an easy L'Hopital's rule problem to check that the limit as t approaches 0 is in fact 0 in this case. So I won't do that. Okay, so the long and short of it is this whole thing goes to 0, which leaves us with this integral. So this is going to be minus m plus 1. Now we can take the antiderivative, which puts another m plus 1 in the denominator. And then we're evaluating t from 0 to 1, which obviously gives us 1 over m plus 1 squared, and that whole thing is negative. Okay, great. So now we've established this third bullet point, and we're ready to move on to this fourth, which involves the Dirichlet eta function. In other words, the alternating Riemann Zeta function and the Riemann Zeta function itself. So let's see how this is going to go. So we can say, well, let's just start with the left-hand side. So eta of s is equal to the sum n equals 1 to infinity of negative 1 to the n over n to the s. So notice this is the sum over all even and odd terms. Sorry, this should be into the n minus 1 up there. So now let's split it up into the sum over all even terms and the sum over all odd terms. So I can do that in this way. So this is going to be the sum, n equals 1 to infinity. And now I'll just put odd here to say that I'm summing over all odd terms of negative 1 to the n minus 1 over n to the s. And now I have plus the sum n equals 2 to infinity, and I'll put even here to say that I'm summing over all even terms. And now I have minus 1 to the n minus 1 over n to the s. Okay, now we can do some simplification. Notice if we're summing over all odd terms, n is odd, which makes n minus 1 even, which means we can turn all of these into a 1. Great. Positive 1, I should say. And then here, n is even, which makes n minus 1 odd, which means we have negative 1 to an odd power, so we can turn all of these to a negative 1, and I'll do that in the following way. So I'll just bring the minus sign out front. Now from here, what I want to do is add and subtract this second term to this right-hand side of the equation. So in other words, I'm going to add the sum n equals 2 to infinity over the even terms of 1 over n to the s. And then I'm also going to subtract n equals 2 to infinity over the even terms of 1 over n to the s. Okay, great. But now, notice if I add all of the odd terms with all of the even terms, and it's no longer alternating, then that's just going to give me the sum of everything. So I'll put the sum n equals 1 to infinity, and I'll put all here, just to reiterate that I've got the even terms and the odd terms, 1 over n to the s power. And now I have minus 2 times the sum over all the even terms. So that's going to be the sum n equals 2 to infinity over all of the even terms of 1 over n to the s. But notice, I can re-index this thing. Since I'm going over only the even numbers, that means I can replace n with 2n and then sum over everything. So here's how I'll do that. I'll erase even. I'll put a 1 here. We're going to sum over everything. And then I'm going to change this to 2n to the s power. And notice that's exactly what I had before. It's just I've indexed it slightly differently. Okay, great. But now what I want to do is notice that this guy right here is just the Riemann Zeta function evaluated at s. And then I'll simplify this a little bit more. Notice I can bring a 2 to the s out of the denominator here, which gives me 2 to the 1 minus s. I've got a 2 to the 1 there, and then a 2 to the s in the denominator. And now I have the sum, n equals 1 to infinity, of 1 over n to the s. But again, this guy is just the Riemann Zeta function. So this gives me the Riemann Zeta function evaluated at s minus 2 times 1 minus s, the Riemann Zeta function evaluated at s. But I can easily factor a Riemann Zeta function out of that, and that gives me 1 minus 2 to the 1 minus s, and then the Riemann Zeta function evaluated at s. Good. And that establishes this fourth bullet point. And now we're ready to move on to our main result. So the first thing that we'll do is we will change this function natural log of 1 plus x over x into that integral which is on the left, and the same thing for the natural log of 1 plus 1 over x squared. So that's going to change the single integral into a triple integral, and it'll look like this. So we'll have the integral from 0 to infinity, 0 to 1, and then another integral from 0 to 1 of, now it looks like the integral of this times this. So that's going to give us 2z over 1 plus xy, and then z squared plus x squared. And then let's get the order right. So this is going to be dy, dz, dx. Okay, fantastic. Now the next thing that we want to do is change the order of integration to put the infinite integral on the interior. And so there's like a theorem that says when you can change like the order of integration in this case, and I'll let you guys look that up if you're interested. So that's going to give us the integral from 0 to 1, the integral from 0 to 1, the integral from 0 to infinity of twice z over 1 plus xy, and then z squared plus x squared, and now we have dx, dy, dz. So we've got something like that going on. Now the next thing that I want to do is look at this integrand as a function of x, and notice that it's a rational function in x, and so that really screams that maybe we should do some sort of partial fraction decomposition. So that's what we'll do. So do a partial fractions. So let's take 2z over 1 plus xy times z squared plus x squared. And notice we're going to want to write that as a over 1 plus xy plus bx plus c over z squared plus x squared. So recall, here we are viewing x as our variable. So we have this linear term in x right here, which means we need a constant on the top. Then we have the quadratic term in x right here, which means we need this linear term on the top, just by standard kind of calculus 2 tricks. Now what I'll do is I'll clear the fractions, and that will lead me towards some sort of equation that I can solve. So clearing the fractions, and then I'm going to change the left and the right hand side of this. We get the following. So we're going to get a times z squared plus x squared plus bx plus c times 1 plus xy equals 2 times z. Okay, so we get something like that. But now notice we can go ahead and multiply out this left-hand side and then look at the coefficient of x squared, the coefficient of the linear term, and then the coefficient of the constant. So let's just look at what the x squared coefficient is first. So notice the x squared coefficient times first is a, because we get that from a times x squared, and then it's going to be b times y. We get that from bx times xy. So b times y. There's our coefficient of the x squared term. Now let's go ahead and look at the coefficient of the x term. So all the coefficients from the x term we get from this bit right here. So notice the x term we'll get from bx times 1, so that will give us b. And then we'll also have c times y for the next bit. So we get that. Okay, good. But now let's go ahead and look at the constant term. So for the constant term, we'll have a z squared. So that's from this multiplication right here. Recall that z is a constant with respect to this decomposition. And then we have plus c from this second term. Okay, great. So that gives us all of this is equal to 2z. But now what we want to do is equate coefficients. So let's think about this right-hand side as 2z plus 0 times x plus 0 times x squared. Okay, great. So I'm going to clean up the board, and then we'll kind of look at what system of equations we need to solve based on this large polynomial equation. So picking up from the last board, we were using this partial fractions decomposition, and we did all the multiplication out, and that gave us a large polynomial. I have extracted the x squared term, the x term, and the constant term, and that gives me these 3 equations. So let's look at the best way to do this maybe. So since this is our most complicated equation, it has a and c in it, maybe we'll take these 2 equations and eliminate the b, so it has to do with a and c. So maybe we'll do equation 1 minus y times equation 2. So in other words, this equation minus y times this equation. So let's see what that gives us. That's going to give us a minus c times y squared equals 0. Because notice our by minus by will cancel. So we get a minus cy squared equals 0. But notice that tells us that a equals cy squared, which gives us a way that we can solve for c pretty easily, just plugging it into here. So let's go ahead and plug this into this equation, and that is going to give us cy squared z squared plus c equals 2z, but we can factor a c out of this, and we get y squared plus z squared, y squared times z squared plus 1 equals 2z. In other words, we have c equals 2z over 1 plus y squared z squared. Great, so we have that value for C. So I'm going to go ahead and write that over here, and so we can erase the board and continue on with the rest of the calculation. So y squared z squared. So great, we've got our value of C, and now I'll erase the board and we can use that to find the values of A and B. So on the last board, we figured out what C is, but now notice that's going to very easily allow us to figure out what A is by this equation that we got on the last calculation. So notice A is going to be this guy times y squared. In other words, it'll be 2 y squared z all over 1 plus y squared z squared. Okay, good. And then notice that by this equation, B is equal to negative cy. But that means that we can write B equal to negative 2yz over 1 plus y squared z squared. So we've got something like that going on. But now what we can do is take all of these values for A, B, and C and plug them in to this partial fraction decomposition, and that will allow us to change this box into something that's maybe a little bit simpler. Okay, so I'll erase the board and I'll do that all in one step. Okay, so we just did an extensive partial fraction decomposition that decomposed this guy into this kind of larger product, which seems like it might be a little harder to work with, but actually it's quite a bit simpler given that we have some easier functions to integrate. Okay, so let's first notice that our innermost integral is with respect to x. So that means x is the variable, and also notice that this big term out front only depends on y and z, so that's a constant with respect to the innermost integral. Okay, so now I want to tackle these one at a time. So I've got the integral from 0 to 1, the integral from 0 to 1, and then we need to integrate this thing right here, so let's see what that is. So notice 2y squared z is a constant with respect to x, so we only need to integrate 1 over 1 plus x times y, and we actually did that as we were proving this bullet point, so I won't bother with it. But what we'll end up getting is a new y in the denominator, which will cancel that y out, and that will give us 2y z times the natural log of 1 plus x times y. Okay, so I'm going to go ahead and underline this in purple and this in purple just to see where it came from. And let's notice, if you take the derivative of this with respect to x, then the interior of the natural log goes downstairs, and we've got to multiply by the derivative of that, which is y, which gives us a y squared. So we are good to go here. Okay, great. Now, let's look at this next one. So this is going to be plus twice. And then this is actually kind of a well-known integral, which is on many integral charts, or you can derive this on your own. This is an inverse tangent, and it's, in fact, the arctan of x over z. So again, I'll let you guys check that those are, that's the correct antiderivative. Okay, so now let's look at this one, but notice that's also going to be a natural log, because if we take the derivative of this denominator, we get something that looks like the numerator. So this will in fact be minus y times z times the natural log of x squared plus z squared. So let's make sure that that is right. So notice if we take the derivative of that natural log of x squared plus z squared, a 2x is going to come out in the numerator, then x squared plus z squared are going to go downstairs. Okay, so that's what we get, and now we need to evaluate this from x equals 0 to infinity and then do a dy dz integral for it. So moving on, I'm going to combine this purple term and this yellow term together, and I'm going to first notice that they have a yz as a common coefficient. This one has a 2 as an extra coefficient, but I can bring that in and square it using natural log rules. So this is going to give me the integral from 0 to 1, 0 to 1. I still have my 1 over 1 plus y squared z squared out front. And then here I'll have y times z times the natural log of 1 plus xy quantity squared over x squared plus z squared. Okay. And then this is going to be plus twice inverse tangent x over z. Okay, good. And now we need to evaluate this from 0 to infinity. Obviously, some limits are going to occur as we do that, but we'll talk through those. So as x approaches infinity, so I'll circle that in purple, the interior of this becomes essentially x squared y squared over x squared. Great. But notice that x squared in the numerator and the denominator will cancel, which tells us that this whole thing charges off to the natural log of y squared. Okay, good. Now let's look at the second term. So as the argument of the inverse tangent goes to infinity, it's well known that the output is pi over 2. So I'll just go ahead and write that. That's pi over 2. Okay, so now I'll circle in yellow what's happening as we let x go to 0. So as x goes to 0, notice this thing is going to turn into the natural log of 1 over z squared. So that's even easier to see. And then here, as x goes to 0, this term is going to go to 0. Okay, good. So now I'll put all of those into their respective places and bring that to the top, and then we'll continue on. I've plugged in all the appropriate limiting values, and we have the following integral to work with. So it's a double integral, 0 to 1, 0 to 1, 1 over 1 plus y squared z squared, and now we have yz times the quantity, natural log of y squared minus natural log of 1 over z squared plus pi. Recall that this was 2 times pi over 2 from that inverse tangent limit, but I've multiplied that together. Okay, now the next thing that I want to notice is that this natural log of y squared can be written as 2 times the natural log of y using exponent rules. And then also this natural log of 1 over z squared, well, I can turn that to a plus, and then this is going to be 2 times the natural log of z. For a similar reason. Notice that's really the natural log of z to the minus 2, but I can bring that minus 2 out front, and that cancels that from a minus to a plus. Okay, so now let's see what we have. So that's going to turn into the integral from 0 to 1, 0 to 1 of 1 plus y squared z squared, and now we have 2yz natural log of y plus 2yz natural log of z plus pi dy dz. Now the next thing that I want to notice is that this guy right here switches into that guy right there if you switch y with the z. So in other words, if we take this term and we switch y with z, one of them turns into the other one. So that means there's some symmetry between how y is acting inside of this term and how z is acting within this term, which means when you do their integration, they will be the same. Let's just notice that. So after integrating, these give the same value. So in other words, we might as well only deal with one of them. So let's go ahead and keep this one because y is before z in alphabetical order, although there's no real reason. But that means this 2 is going to turn into a 4, and we're left with the following integral. So 0, 1 to 0 to 1 of 1 over y squared plus z squared plus 1, and now we have 4yz natural log of y plus pi, and then dy dz. Okay, great. Now, the next thing that I want to do is change this term right here using geometric series into an infinite sum. So let's recall maybe that 1 over 1 minus u is equal to the sum n equals 0 to infinity of u to the n. And so that's what we'll use here, but in this case, u will be equal to minus yz quantity squared. Great. So let's see what that gives us. That's going to give us the integral from 0 to 1, the integral from 0 to 1 of the sum n equals 0 to infinity of minus 1 to the n, y squared to the n, in other words, y to the 2n, z to the 2n for the same reason. And then we have this is multiplied by 4yz natural log of y plus pi, and then we have dy dz. Okay, so the next thing I'll do is I'll bring that to the top, do a very, very slight simplification along the way, and then we'll go off to the next step. So I've brought that previous expression up from the bottom of the board, and I've factored some constants out. I've exchanged the order of summation and integration, which we can do because this is absolutely convergent, and I've broken it apart into two sums. Another thing that I've noticed is that the integrand for this first double integral is a function of y times a function of z. So notice it's y to the 2n plus 1 times natural log of y, that's our function of y, and then it's z to the 2n plus 1, that's our function of z. And then likewise, the integrand here is also a function of y times a function of z, but that's a little bit easier to see even. So anytime you have an integrand that's like this inside a double integral, you can split that apart into a product of two single integrals. So let's see what that gives us. So this is going to give us 4 times the sum n equals 0 to infinity of minus 1 to the n. Now let's look at our y integral. That'll be the integral from 0 to 1 of y to the 2n plus 1 times natural log of y dy. Great. So I'm going to go ahead and put purple brackets around this. This is our y integral. And then we'll also have a z integral, which will be from 0 to 1 of z to the 2n plus 1 dz. Great. So now we've got two like calculus 2 type integrals which are fairly simple. Now this is going to be plus pi times the sum n equals 0 to infinity minus 1 to the n. But notice if we pull those apart into two integrals, they're actually the same integral with just a different variable. So that means we might as well just write it in the following way. This is the integral from 0 to 1 of y to the 2n dy, and then times that same integral with just y's replaced with z's, but that means they're the same, so I can just change that to this integral squared. Okay, great. But now I've got some fairly simple stuff to do. So this is going to be 4 times the sum n equals 0 to infinity minus 1 to the n. Now notice this purple integral is actually our third bullet point. So we can use that directly where m is replaced with 2n plus 1. So like I said, m is 2n plus 1. So that's going to give us minus 1 over 2n plus 1 plus 1, in other words, 2n plus 2 squared. So that's what we get for this purple guy. So here, maybe I'll put that in purple. And then notice here, I just do an antiderivative, which is really the power rule. That gives me 1 over 2n plus 2, z to the 2n plus 2, evaluated from 0 to 1. Good. So that's actually easy to do, so I'll just write that here kind of in the margin. That is going to go to 1 over 2n plus 2. Notice when you plug in 1, that's what you get. When you plug in 0, you get 0, so that's all you have. Okay, now here we're going to have, this is plus pi, the integral from n equals 0 to infinity, sorry, the sum, minus 1 to the n, and then this is very, very clearly 1 over 2n plus 1 squared. So now we can start to simplify this. I'm going to bring this minus sign out front. That's going to give me a minus 4. Now I'm going to have the sum n equals 0 to infinity of minus 1 to the n over 2 n plus 2 to the third power. Okay? Then I'm going to have this as plus pi times that sum right there, but that sum actually has a name. It doesn't really have a closed form unless you use this name for the closed form, and that is g, where g is Catalan's constant. So this is also the Dirichlet beta function evaluated at 2, if you want to look that up. Okay, good. So now we can simplify this a little bit. So first thing I want to do is bring a 2 out. So notice if I bring a 2 out of the denominator, I have 2 cubed, which is 8. That's going to cancel with this to give me a minus half. So here we have minus half. The sum n equals 0 to infinity of minus 1 to the n over n plus 1 plus pi times g. Okay? But notice that this guy right here is just a very, very simple re-indexing of this Dirichlet eta function. And in fact, it's this Dirichlet eta function evaluated at 3. Great. So that means here I get minus 1/2 the Dirichlet eta function evaluated at 3 plus pi times g. But now using our final formula that puts it in terms of the zeta function, that's going to be minus 1/2, 1 minus 1/4, because notice we have 1 minus 3, so that's going to be 2 to the minus 2 of the zeta function evaluated at 3 plus pi g. In other words, this thing is pi times the Catalan constant minus 3 over 8 times the zeta function evaluated at 3. And that is the value for our goal integral, which finishes this video.